Hi, my name is Armando Diaz, and this presentation is for the Advanced Computer Network class. I will be reviewing the paper titled Wide Area Network Autoscaling for Cloud Applications. Now, this presentation is structured as follows. First, we will review the problem statement. Second, the related work. Third, the proposed solution. After that, the results. And at the end, we will review the future work. Let's go ahead with the problem statement. Now, there exist orchestration tools such as OpenStack for virtual machines or Kubernetes for containers. Um, if we focus on Kubernetes, for example, Kubernetes provide a versatile and robust way to host application at scale. And one of their key features is autoscaling, which automatically adjusts cloud resources such as compute, memory, storage, in order to adapt to the demands of applications. However, these tools have some limitations. The first one is network scalability, which is limited by the cloud infrastructure of data center. The second one is called intercluster connectivity, which is provided by a wide area network called WAN. However, this one is very expensive and it comes with limited capacity. The third one is lack of communication between the cloud and the wide area network. So there is not currently a system or tool that can communicate the how the network is behaving in the cloud and the wide area network to just trigger some auto scaling capabilities. So auto scaling, the last one is auto scaling events detected by the orchestrator, like Kubernetes, only propagate within the compute domain and not really through the network. And so the authors wanna come up with a new approach that can detect changes on the network traffic, and based on these changes, just trigger some events that will scale the resources of the network. So, related work, there are three main approaches. The first one is reactive network autoscaling. This one is very simple. It just monitors the network traffic, compute an average, and after that, it triggers autoscaling events if the average exceeds a threshold. So let's say we have a certain bandwidth, and if that bandwidth is exceeded, we will just trigger an event that will auto scale the bandwidth for that particular network. There is another approach called application aware networks, and this one extends the socket API. It adds other parameters that allows the socket to know which applications will need to scale depending on certain events. The third one is called service meshes. This one merge a layer 3, which is the IP stack, with layer 7, which is the application stack, to increase performance and application awareness of the network. So as we can see here, there is some communication between the application and also the IP stack. Now the proposed solution, um, as we can see here, we have a diagram on the right. In this diagram, we are trying to display two main components. So the first one is extract. The first one extracts the network requirements from the application by using the orchestrator API. So let's say Kubernetes. How this is going to work. So let's say that you have an application, a web application or mobile application, whatever you want to call it. And what we are going to do is to add annotations of these workloads inside our Kubernetes and use this metadata to automate tasks and automate triggers that will be detected with this application. And since we're using a wide area network, there are some capabilities that will allow us to communicate between the network and the orchestrator using an API. And through this API, we can just send these triggers. So the second step is send information to an SD-WAN controller. Let's say, for example, that we detected that the bandwidth is not enough, so we request more bandwidth. Or another example, it can be that we wanna just change the paths to the requested traffic profile, so we can just reduce the traffic in one of those paths and just have the traffic more distributed in the network. Now, what are the benefits of this? The first one is that if you have communication between, you have some metadata of your application that tells you how that particular application is gonna auto scale the bandwidth. That will allow the network auto scaling to first uh, prevent some surges in the network load and immediately increase capacity. The second one is um, also increases the network capacity shortly before surges in demand. So that means even before the bandwidth is overloaded, we will be able to just increase the network capacity, which is gonna increase the performance of our applications. Then the network dynamically matches the requirements of applications, and this is due to the metadata that we are gonna have in this case of our application and our orchestrator tool. And then overall, this will achieve just higher efficiency in resource utilization. Now let's go with the results. On the right side, we have um, the experiments that were performed in this paper. The blue line means the traffic, as we can see here. The orange line is the target replicas, and this means this is controlled by Kubernetes. So let's say you start with this number of compute resources or workers, and then the Kubernetes is gonna just increase the number of workers or the number of replicas so it can support more compute. And we also have the line green, which is the virtual circuit bandwidth. This is usually fixed, at the beginning. One of the main challenges of not having a network auto scaling is that developers used to oversize the network. So they put very high limits, so it never reaches the network. But obviously, by doing that, you are paying the cost is just a lot higher. So in order to minimize that cost, we wanna come up with this network auto scaling. The first, as we can see here, at the beginning this virtual circuit bandwidth is fixed is stable, and when the tire replicas, it starts increasing and reaching the bandwidth, before it reaches that bandwidth, just the auto scaling is gonna increase the the resources of the network. So that way, we can just support more clients. We can, I mean, the network is not gonna be overloaded, and obviously the performance of our application is gonna increase. So this is pretty much how it works, the vertical network autoscaling, which is just increasing the number of computers that are gonna be supporting our application. Now let's go with the horizontal network autoscaling. Um, in this one, um, as we can see here, this one has two different tunnels. Um, so that means that we have more than one computer um, just running. So let's say that the first computer is going to have a bandwidth of 3 megabytes, and let's say that the other one is going to have a bandwidth of 1 gigabyte. These two different tunnels, or the application is going to be changing using depending on the traffic and on these different tunnels. And how it's going to do that, that's going to be performed by the annotation which are defined in the application and are consumed by Kubernetes. So once Kubernetes detects that the threshold is reached, it automatically switches from one tunnel to the other one. So this is another example of how this approach is behavioring. Now let's go with future work. There are a lot of open challenges with this approach, and the first one is the bandwidth estimation. Um, this is because the authors first, they assume that an increase in CPU utilization is always going to translate to an increase in the required bandwidth. And these are just simple estimations and simple rules that are set in under the application. However, this traffic can be estimated. One of the approaches is called time series, which I believe is gonna use just previous data to estimate how much traffic is gonna come in a certain period, and then just based on that increase the bandwidth. The other one is application diversity. Um, this 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 approach, or the experiments, were mostly assigned to a single tunnel. This means that we are gonna only have like one let's say one computer where we are gonna be communicating. However, in real world scenarios, that's not the case. We have thousands of applications that are connecting to multiple tunnels, and that share the same connection. So we there are some work that can be done under the application, the number of tunnels and shared memory. The other one is called network topology. For this one, more information about the traffic is required to determine which virtual circuit needs additional bandwidth. So because we are adding some metadata about the application to control when the network needs to be increased, there are some aspects of the network that that is not stored on the metadata. So if we want to use multiple tunnels, we want to use and use the same connection. For example, we need to create like new topology about our network, just to classify, see over which event, how each event is gonna be attack, how each event is gonna be used for network autoscaling. And the last one is called billing model, and this is because most of the time the bandwidth is provision rather than being on demand. When this new model that is gonna auto scale the resources of our bandwidth, we will need a solution or an approach to know how much we are gonna uh, how much that is gonna cost in terms on consumption. So this is obviously an approach that is seen to be implemented in the cloud, and we aim to um, charge differently if you have some bandwidth which is provision, and if you will have like a different price if you know that your bandwidth is gonna be on demand, which is it should be a lot less. And this is pretty much everything. Thank you.